And okay, we're on.
All right, good afternoon, good evening, everyone. Thanks for joining us. We're going to spend this session talking about the Quittapahilla Watershed Water Quality Monitoring Program, and specifically, we're going to talk about Streamflow and how we get Streamflow monitoring. So just stop me in the middle of anything if you have a question. So Mike, it looks like I've got a message that says the host has disabled participant screen sharing.
All right, let me change that. All right, you should be good.
Okay, let's see. Share screen. All right, great. Thanks, Mike. Okay. So, here we go. So we have set up a Quittapahilla Watershed monitoring program, and tonight we'll be doing classroom training on Streamflow. This is our November session. We did the same session a year ago or so, but won't hurt to do it again. So Mike, do you see these pictures over here of all of us?
Yes.
Can we get rid of that?
That's on your screen.
Okay,
you need to go up to the upper right where it says view.
Got it. Got it, thanks. Okay, so give you an overview of our monitoring program. We do really three basic things. We look at habitat and geomorphology of the streams. This is done under the guidance of Rocky Powell. Rocky Powell is a consultant, very knowledgeable in aquatic ecology. And he's been doing this primarily with summer intern students in the past. There's also a biological monitoring component. This has been done by Dr. Rebecca Urban and her students at Lebanon Valley College. And we're doing water quality monitoring, and that is being done by volunteers like you folks on the line. So I want to talk about the water quality aspect of it. The overview for the water quality part of that includes streamflow monitoring. We have 5 locations where we're doing streamflow monitoring. And there's a 6th location at the Palmyra Belgrove Road where we don't do that because the US Geological Survey has a streamflow monitor there and we can use the data from that point. We also do fixed point sampling. This is all 6 locations done by our volunteers. And we hope to do some special studies, primarily with summer interns, particularly with dissolved oxygen and temperature in the stream. Here's a map showing the location of our 6 sampling sites. This is the town of Lebanon, city of Lebanon. This is the Swatara Creek. And here's the Quittapahilla flowing parallel to Route 422 for most of the way, and then on down to the Swatara Creek. So we have a station here in Cleona on the Quittapahilla and a station down here at the Palmyra Belgrove Road on the main stem Quittapahilla. Then we have 4 stations on each of the major tributaries, the Snitz Creek, Beck Creek, Bachman Run, and Killinger Creek. So 6 stations, and here's a list of them, and we have numbered them somewhat intuitively. So for our water quality monitoring, our schedule includes classroom training on Streamflow. That's what we're doing tonight. We will do a session on classroom training on water quality sampling. That'll come later. We'll need a field work session to install our stream gauges. Guess what? That's already done. We did that last fall before the COVID pandemic became too bad. So we did that already. We need to do field training on Streamflow. That'll be in the field at a later date, and field training on water quality sampling. And then we can begin our sampling. So it's a lot of work to do before we even get started. But today, we're going to focus on Streamflow basics. We'll talk about what is Streamflow, why is Streamflow important, how do we measure it, and what's the role of the volunteers. So what is stream flow? It is the volume of water moving past a point during a specified period of time. So volume is measured in cubic feet. You can imagine a box that's 1 foot on all sides. That's a cubic foot. And time is measured in seconds. So the volume of water is measured in cubic feet per second, or written out in mathematical terms, cubic feet per second. Also abbreviated very frequently as CFS, cubic feet per second. Now we'll talk about stream flow, of course, but when we talk about flow, we also use the term discharge, which is the same, is their equivalent. It's also the same as the volume of water, and it's frequently denoted by the term Q. Why is it important? Well, it's used for flood forecasting. The U.S. National Weather Service takes data from stream flow locations across the nation, and they predict how high the flood will be. We can use it for engineering calculations. Engineers want to know how high off a creek should they build a bridge. We use it for dilution of pollution. When I was in graduate school, there was a saying that says, dilution is not the solution for pollution, but in fact, all of our effluents go into a stream where they are diluted, and that's part of the calculus of how much effluent can be released into a stream. Stream flow is important for calculation of loads, and we'll talk more about that later, calculation of yields, and influence on water quality. So continuing with this theme, why is it important? We need to talk about a TMDL. A TMDL stands for total maximum daily load. Now, check this term out, load, because that's just what we're going to be talking about. There was a TMDL prepared for the Quittapahilla watershed in the year 2000 by the Pennsylvania Department of Environmental Protection. Here is a photograph of the first page of the document. And what they found was excessive sediment and nutrient loads have been identified as the primary causes of impairments. So that's what we need to focus on in our monitoring program, sediment and nutrients. So because of this excessive nutrients and excessive sediments, the Quittapahilla and its tributaries are listed as impaired. They're on the 303D list of impaired streams. This is a list of all the impaired streams in the state prepared by the Pennsylvania DEP. So we're talking about loads, so let's figure out how we calculate loads. Load is equal to the concentration times the flow. So the concentration of whatever, phosphorus, nitrogen, sediment, times the flow. Mathematically, L is equal to C times Q. And for yields, yields is similar, but the yield is equal to the load divided by the drainage area. This yield is important because it will allow us to compare one site to another site. In other words, let's suppose we had a load for Snitz Creek and a load for Bachman Run. Snitz is a larger drainage area than Bachman Run by a good amount. So if we just compare the loads, that wouldn't be a fair comparison. So instead, we'll compare the yield, that is the load divided by the drainage area, and that would allow us to compare Snitz to Bachman or any other locations as well. Let's talk about flow and water quality. Higher flows carry more sediment. Higher flows dilute point source effluents. Higher flows dilute groundwater inputs, and we're going to talk about each of those a little bit. Here's a schematic representation of the influence that water has, that volume of water has on water quality. And you can see that for suspended substances, the concentration of the suspended substance increases as stream flow increases. This is holds true for sediment and for anything that's attached to sediment. For example, phosphorus, metals, organic compounds. Doesn't take too much imagination to figure out that high flow carries more sediment. And this is a photo from a farm field, and I'm not sure where, but I've seen similar photos than this for Lancaster County. So the implications of this influence of flow and water quality, let's just do a little example. Think about determining trends in water quality. Imagine that Doc Fritchie Trout Unlimited and the Quittapahilla Watershed Association install 3 stream bank stabilization projects over the next 2 years. This is highly likely. We probably will. We know these projects result in a reduced sediment input from bank erosion, but we need to prove it in order to get more funding. So we do our water quality monitoring, and we find that the load of sediment has not decreased like we thought it would at all, but it has increased. Perhaps it is because we initially sampled at low flow, and following the installations, we sampled at higher flows to get a higher load. So we got to really be careful and measure flow discharge every time we take a water quality sample. Sticking with the same theme, the volume of water has an influence on water quality. And here's a schematic representation for dissolved substances. This is just exactly opposite of what we had for suspended substances. For dissolved substances, the higher the flow, the lower the concentration. This holds for things like calcium and magnesium, chloride, sulfite, nitrates, and point sources. So if you've got a point source, I think I have a slide here. If you've got a treatment plant effluent, that's a point source going into the stream, and the higher the flow, this is diluted. The point source effluent is diluted at higher flow because this volume of flow is pretty well constant, but the volume in the stream changes. So you can get a dilution factor. All right, so let's revisit the reason that stream flow is important: floods, engineering calculations, dilution pollution. And we talked about we need stream flow to calculate loads. We need stream flow to calculate yields. And we know that stream flow has an influence on water quality. So stream flow is quite important. How do we measure stream flow? Stream flow is equal to the cross-sectional area times the velocity in a stream. So cross-sectional area is simply the width times the depth. You measure the width using a tag line or a tape measure. Using the depth, measure the depth with a yardstick or a measuring rod. And the velocity is the rate of flow. You measure that with a velocity meter. So here's a tape measure that you can use to measure the width of the stream. And we have those on hand. Here's what's known as a top set weighting rod, and it has a pygmy velocity meter attached. So this is the rod here. It's propped up against a barbecue grill here, but this is the rod. This is the velocity meter that's attached to the rod. This is a headset. What happens is the velocity meter whirls round and round. Every time it goes around, it makes an electrical connection, and you hear a click in the headset. So that's how that works. We have a couple of those. So velocity meters, we can buy one from Global Water, costs $1,000. We can buy one from Hawk, costs almost $6,000. We can buy a price current meter, $800. Or we can use a little pygmy current meter like this one. There's a quarter for size. It's a little baby thing. We can measure the velocity with the current meter, and the cost is zero because we have 3 of these that were donated to us from the US Geological Survey. Why would they do that? Because this meter is now outdated. They measure these things, they measure velocity these days using acoustic Doppler meters. So this is old technology, but it's still worthwhile and useful. So back to how do we measure stream flow? Imagine a stream. Here it is. It's a perfect rectangular cross section. It has laminar flow. So the volume of flow is equal to cross-sectional area times the velocity. Let's do a calculation. Let's say the cross-sectional area, say the width of the stream is 8 feet and the depth is 2 feet. Then the cross-sectional area is equal to the width times the depth, 16 feet squared. Then we take our little velocity meter and we measure the velocity. Let's say it's 2 feet per second. Then the volume of flow is equal to 16 feet squared, the area, times the velocity, 2 feet per second, is equal to 32 cubic feet per second. CFS, 32 cubic feet per second. But the problem is cross sections are not perfectly rectangular and straight in shape. Flow is not laminar. So we subdivide the stream into subsections and measure the flow in each subsection. And here's a little schematic for that. So we divide the stream into little short sections like this, and we measure the width and depth of each one of those, and we measure the velocity in each one of those. And then we can get the calculation, we can calculate the flow for that little subsection. If we do that for all these subsections across the stream, we can add them up and get a total flow for the stream. Now, if you take a look at this, can you see my pointer, Mike? Willie, can you see my pointer?
No, I can't see it.
Can't see my pointer.
Oh, yes, I can, sorry.
Okay, great. So if we do this, this little section here is calculated in when it's not really a stream, but this little section here is calculated out when it is a stream. So it's not exact, but it's pretty darn close, especially if you got a smooth bottom like this part here. Okay, so let's move along. You sum the flow from all the individual subsections to get a total volume of flow. So how do we do it? We measure the width of the stream, divide the stream into equal width sections, determine the width of each section, measure the depth of each section at the center point of the section, measure the velocity at 6/10 the depth. I'll talk about that in a minute. And you calculate the flow for each section, sum all of the flow calculations to get the total flow. 6/10 the depth. The vertical velocity profile under normal conditions tends to have a shape like this. We can use this relation to compute a mean vertical velocity based on measurements at certain points in the vertical. And what the USGS has found is that the point at 6/10 of the depth is kind of the average for all the velocities. You get a higher velocity at the surface than you do at the bottom. So 6/10 is the average. So an example would be, suppose the stream depth is 8/10 of a feet. 6/10 of the depth is 0.6 times 0.8 equal 0.48 feet. Just set the velocity meter 0.48 feet. So for sometimes when the stream is greater than 2 feet in depth, we measure velocity at 2/10 and 8/10 the depth and average the two. And there's a calculation for that, which we don't really need to go through, but it's more accurate for deep water. And here's the story behind that. 6/10 of the depth whenever it's less than 2 feet, and measure at 2/10 and 8/10 when it's more than 2 feet, and average those two. So where do we measure stream flow? The best location is a straight reach having uniform flow from bank to bank and a smooth bottom. Well, you don't find that very often, but you do the best you can. It's best at a site where there are no eddies, because eddies obviously are going to flow upstream instead of downstream. And you measure away from the influence of bridges and other obstructions to as best as you can. And always do it concurrent with water quality sampling, because it's so important in interpreting our water quality results. All right, every time we take a stream flow measurement, we need to record a water level reading from a staff plate at that station. Staff plate, what is a staff plate? Staff plate looks like this. It's just a ruler, but it's turned on its side. These are two different ones. That's one and that's one. So a ruler turned on its side is a staff plate. Here are pictures of staff plates. This is one like we just saw in the photo. And they're mounted on trees, they're mounted on posts, they're mounted on bridges or wherever. Here's a picture of one mounted on a wing wall for a bridge, and that's the way most of ours are also. There's the staff plate on the wing wall for this bridge. So the reason we need a staff plate is to construct a rating curve. The story is that we take many manual stream flow measurements, and we plot the stream flow against the gauge height or the stage. So we're recording gauge height at that staff plate every time we take a manual stream flow measurement. And then we can graph the stage in feet against the discharge in cubic feet per second. And if you plot that on log scale, it comes out to be nearly a straight line, especially in the mid-range, but it depends somewhat on the shape of the channel also. So that's why you have to do this rating curve for every station that you measure. But we need continuous stream flow measurements, and I'll tell you why in a minute. We can't measure stream flow continuously because you can't be out there with that little velocity meter. But we can measure water pressure continuously, and water pressure changes with gauge height or with how deep the water is. So we can correlate water pressure with gauge height, and then we can measure stream flow and relate that to the gauge height. That's the rating curve that I just showed you. And then you can develop a relation between water pressure and stream flow. And so with that, well, how do we do that? We measure water pressure using a pressure transducer. This is a pressure transducer. Water pressure, the deeper the water, the higher the pressure. So this little device here, this is made by the Onset Hobo company. I don't know if you can read that, Onset Hobo. It's a water level logger, and it measures water pressure. And the deeper the water, of course, the higher the pressure. We have 5 of these things already installed. And most of our installations look like this. We have a staff plate mounted to a wing wall. There's an example. And then we have a pipe, what we call a stilling well. And inside the stilling well is the pressure transducer, and it's down in the water. And so the higher the water, the higher the pressure. And the information from that pressure transducer is stored in a data logger, which is also in the stilling well, but it's above water level. So that's basically what we have at each of our 5 locations, and the USGS has a similar device at the 6th location. And then from that, we can develop an annual hydrograph. Here's for the Quittapahilla Creek near Belgrove. This is for the year 2019. Remember the Quittapahilla Creek near Belgrove, it's the Palmyra Belgrove Road. I told you the USGS has a station there. This is the hydrograph from their data. And looks like in early November, like November the 1st, there was quite a flood, 1,000 cubic feet per second. We'll be able to manufacture these kinds of hydrographs from our data, assuming everything goes as planned. So remember that suspended substances go higher with stream flow. But if we have a record of stream flow for any day, then we can estimate the concentration of a contaminant in water based on the stream flow. We've seen how stream flow is related to water quality. So if we could measure stream flow continuously, then we would have a pretty good estimation of water quality at a given time. Remember now, load is equal to concentration times discharge. So we can estimate annual loads if we use the daily stream flow values from our hydrograph, We can multiply by the concentration associated with that flow, because there's a relation between concentration and flow. Sum that over 365 days, and we have an estimate of the annual load. And that's exactly what we need to satisfy DEP to hopefully take the Quittapahilla off the 303D impaired list. So for our volunteers, we've got a lot of work to do. We need to install our Streamflow stations, but guess what? We already did that last fall. We need to run levels for Streamflow stations because we don't want these pressure transducers to be at any other level than what they are right now. We don't want them to sink or to rise up or anything else. So we'll do some surveying to survey these things in. Then we'll conduct streamflow measurements. We'll conduct water quality samples. We'll filter some of our samples, put preservatives, deliver them to the lab, and download the data from the pressure transducers, and we'll be able to really give a good accounting of our stream flow, of our loads. Who will do this work? Our volunteers. We have now 9 volunteers. Here you see their names, and I appreciate every one of them. We actually have 2 more that have joined us as of today, Cindy Camp and her husband, who is what? Her husband is, I forget his name, Silva, Greg Silva. So we could add them to the list because they're going to help us day after tomorrow with our invertebrate sampling. So we're really set up pretty nicely, I think. So here's a look at our schedule. We need to have classroom training on Streamflow. That's what we just did the last 30 minutes. We need classroom training on water quality sampling. This will be conducted by DEP staff, and we haven't scheduled that yet, but it'll be coming up before long. We need a field work session to install our stream gauges. That's already done. We did that. We need field training on Streamflow. We tried that, didn't work out well because our instruments didn't work well. So we got our instruments reconditioned, modified, and we'll do this again. Then we'll have some field training on water quality, and we begin our sampling program. So I'll leave you, because we'll be in and out of the streams, I want to leave you with some safety tips. Any stream, even a small stream, can rapidly become too deep or too swift to wade safely. Before entering the stream, confirm that it can be safely navigated. If it's too swift, don't sample. Guess what? Saturday, we went to the Quittapahilla Creek at Garfield Street, and there had been about 2 inches of rain the night before. And we were going to collect invertebrate samples, but it was so swift that we didn't think it was safe. We called it off. We rescheduled it. We're going to do it day after tomorrow, Thursday morning. So if it's too swift, don't sample. It's not worth it. And always use a waiting staff. So I want to stop sharing my screen and ask if there are any questions. Chad, I see you for the first time. Welcome to our group. Gary, you're an old pro. Thanks for joining us. Willie, same to you. And Mary Kate, you're a new volunteer for us. We have a lot of work to do. Next, the next task is invertebrate sampling. Normally, Lebanon Valley College does the invertebrate sampling, but we're taking it over this year because of the pandemic, I guess, for some reason. Dr. Urban can't get the approval to transport her students to the field. So our volunteers are going to do it. Willie will be there. Gary has already helped us out. And we've got other volunteers lined up, Steve Vigo for sure, and probably Cindy Camp and Greg Silva. And then we're going to be doing the same thing again at different locations on Saturday, and we need another volunteer for Saturday. Chad is on tap for Saturday. Chad, thank you for that very much. Willie will be there Saturday, and we need one more volunteer. I've put out a call.
I wish I could, Kent, but we're having a volunteer work day over in the nature park.
Okay.
We're clearing off trails in the Quitty Creek Nature Park, so otherwise I would.
Okay. All right. Well, I think we'll probably be able to get someone. We've got a good group, and they're willing and able. So, any questions at all?
One thing I might want to do, Kent, just as a kind of a little addendum, is to maybe I'll share the screen with the Watershed Association website and where all this information is going to be housed.
Feel free, Mike. Very good.
On the website here. So let me pull that up. So this is the website of the Quittapahilla Watershed Association, and you can see here the left-hand bar is our navigation bar. We're over here on the monitoring tab. So we have it's pretty bare bones right now. Just a summary of the monitoring program, the volunteer team, and our 6 monitoring stations, and the same map that Kent showed. And then there's actually images of each of these stations, so you can see exactly where they are. And then I'm going to have to update this list of volunteers I see, but this is our list of volunteers. And then the data will be housed, at least for now, it'll be housed here as we move forward. And what I can do, Kent, is house this recording in somewhere on this page as well. And we can have maybe a 4th category of instructional material.
Very good. Mike, while we're here, would you please open the quality assurance project plan down at the bottom?
Sure.
So this is a document that I prepared to really guide our whole effort. And Mike, can you scroll down to the table of contents? Or yeah, there we go. So this tells us a lot about the program and about how we're going to be sure that we're collecting good data. Now, volunteer monitoring efforts sometimes don't collect very good data. They don't do the things they need to do. They don't do the quality assurance and quality control. We will. We'll take duplicate samples. We'll send in blank samples to the lab. We'll make sure our equipment's clean. And so we'll evaluate all this and hopefully have not only a complete program, but one that's quality assured as well. So if you care to, please take a look at this document. It's pretty long and a little bit technical, but I think you can understand it. And it's certainly technical in some spots, but take a look at it. I think it'll be worthwhile. And with that, if there are no other questions, we'll bid you for.
Can't just refresh our memories. Collecting, was it monthly, every other month? I forget what the plan was.
We're going to shoot for every other month, Gary, but it's also important that we collect at a range of flows: low flow, medium flow, high flow. Now, high flow is a little bit iffy, but we'll just have to use our judgment. I don't want anybody washing down to the Chesapeake Bay. So if it's too high to wade, don't even try it. Or you could sample from a bridge perhaps, but we'll work at that when we get to it. Yep, every other month, but spread out over a range of flows.
And do you anticipate a start month?
It really depends upon DEP. We need DEP to come through for us to give us our training, explain how to work our instruments, and explain we have to set up an account at the DEP lab, and they give us passwords and they give us information to use that account. And so we really can't start sampling until that. DEP has provided us with a lot of equipment already, sample bottles, filtration units, etc., coolers. So we're in pretty good shape. I need to talk with DEP again and finalize that. Hopefully I'll be talking with them within a week.
Great. So when is is there the next classroom event like this, Kent?
Not scheduled. The next classroom event like this will be information about water quality sampling. Tonight,
Yeah.
we talked about flow monitoring and flow measurement. Water quality sampling is the next in line. And that we need to have DEP present that for us, really.
Great. Okay.
Okay, everybody, thank you so much. Have a great evening. See you on the
Thanks
creek.
so much. All right. I'll stop the recording.
Thanks.
Thanks, everybody. Good
folks.
night.
Good night.